Hello, everyone. Let's start this lesson off with reviewing the mole-gram conversions that we've been doing. So pause this video, copy this problem down, try it out, then unpause the video and we'll go through it. All right, so let's go through this problem. So remember, the first thing we always want to do with these mole-gram conversions is determine how much one mole weighs, right? So list our elements, mg, o, h, count them up, 1 mg. Now these parentheses, don't forget, this little 2 out here applies to everything inside the parentheses, and parentheses always mean multiply. So we've got two O's and two H's. Now we times them by their masses that we round off to the nearest tenth off of our periodic table. So magnesium is 24.3, oxygen is 16.0, and hydrogen is 1.0. So we tally these up and we get 58.3 grams per mole, right? So this, remember, is our gram formula mass, our GFM. Now we're going to use that in our formula. Moles equals grams over GFM, which is on table T, right? So these problems are pretty straightforward, right? We always know the gram formula mass because we figure it out. And then we're either solving for the moles or we're solving for the grams. So in this case, it says determine the mass. So we're given the moles and we're solving for the grams. So let's work through it. All right. So we know it's 2.75 moles equals X is our unknown over the gram formula mass, 58.3 grams per mole. So set our moles over 1 and we cross multiply. And we get 160.325 what? Grams, right? So how do we know it's grams? Because remember, when we cross multiply, moles over moles cancels out, and we're left with grams, right? That's our standard mole gram conversion. Either we're given the moles and we're solving for the grams, or we're given the grams and we're solving for the moles. Not too bad, okay? So for today's lesson, let's take out our math in the mole unit packets and go to page 5 where there are some filler notes about this topic. So we're going to talk about empirical and molecular formulas. So there are two types of chemical formulas. We have empirical formulas and molecular formulas. So we'll start off with the empirical. So the empirical formula is the simplest whole number ratio of atoms in a compound. All right. So this isn't necessarily telling us exactly how many atoms are in the compound. It's just telling us for every one, say, carbon, how many hydrogens are there in a molecule of C6H12. All right. So one thing we want to remember is ionic compounds are always in the empirical formula. So like KCl, Al2O3, MgCl2. And what that means is they can't be reduced anymore, right? Nothing means one. So 1 to 1, we can't reduce any further. 2 to 3, we can't reduce any further. And 1 to 2, we can't reduce any further. So ionics, because remember, we don't have molecules in ionic compounds, so they're always going to be in the simplest whole number ratio. So the molecular formula is the actual number of atoms in a molecule. So molecules, remember, apply to our covalent compounds, right? Non-metal, sharing of electrons. Okay. So those are always a multiple of the empirical formula. So let's look at some examples. So here are some molecular formulas on the left, and I want to try and determine what their empirical formulas are as well. So all you got to do is look at the subscripts and see if they have some common denominator. So 2 and 4 are both divisible by 2. So that would reduce to CH2, a 1 to 2 ratio, right? So that's telling me for every one carbon, there are two hydrogens. It's not necessarily telling me how many total atoms are in the molecule. It's just telling me that for every one carbon, there are two hydrogens. The molecular tells me exactly how many atoms are in the molecule. Now, for something like H2O, 2 to 1, we can't reduce that anymore. So that's already in the empirical formula. So sometimes the molecular formula is already as simple as it gets. So then in that case, the molecular and the empirical are going to be the same, just like the next one, CO2. Now in the next one, C6H12O6, 6, 12, and 6 are all divisible by 6. So when we reduce that, we get 1 to 2 to 1, right? And now same thing with 2, 4, and 2 in the next one. These are all divisible by 2. So when we reduce that, we also get 1 to 2 to 1. So two different molecules can have the same empirical formula. That's perfectly fine. That's just telling us that in both of these molecules, for every one carbon, there are two hydrogens and one oxygen. All right. Now, say you get something like C18H36, and you say, okay, these are both divisible by 9. That would be my greatest common denominator. All right, great. Well, in fact, it's not the greatest common denominator. It would be 18. But say you screwed up like this, then you're going to get 18 divided by 9 is 2, right? C2. Oh, we get C2. H36 divided by 9 is 4. So we get C2H4. So when you screw up and you don't divide by the greatest common denominator, just check your answer and see, can I reduce this any further? And I say, oh, wait a second. 2 and 4 are still divisible by something. They're divisible by 2. So that's going to bring me to CH2. And now I can't reduce that any further. So if you make a mistake and don't divide by the greatest common denominator, just check your answer and see if you can reduce it further. If so, keep going. And eventually you'll get to the simplest whole number ratio. And again, C18H36 and C2H4 both have the same empirical formula. That's fine. It's just telling me that for every one carbon, there are two hydrogens in both of those molecules. All right. So pretty basic stuff. Now, the next thing is a little bit more in depth. It takes a little bit more of a procedure. Okay. So this is determining empirical formula from the percent composition. Now, you can write this on the back of page 5 of your note packet if you'd like. So turn over the page we're just working on. And we could put this on here. All right. So now in this kind of situation, what happens is you get percentages. So we want to determine the empirical formula from the percent composition. So all I'm given is that whatever this compound is, it's 88.8% copper and 11.2% oxygen. So how do I do this? All right. So first thing I want to do is list my elements in a column. Leave a little space in between them because you're going to do the work across. All right. So skip a little more space as well. And then we're going to take note. Step 1 is convert percents to grams. So this is pretty simple. All we got to do is assume that we have a 100-gram sample. All right. So if we have a 100-gram sample and a percent means per 100%, then if I have 100 grams, then if I have 88.8% copper, that means I have 88.8 grams, right? So if we assume that we have a 100-gram sample, all we got to do is take the percents and make them grams, G's, right? So we have 88.8 grams copper and 11.2 grams oxygen. Step 2 is convert those grams to moles, all right? So how do we do that? Well, we use the formula that we've been using. Moles equals grams over gram formula mass. So where do we get the gram formula mass of our elements? Off the periodic table. So we go to the periodic table and we find the masses of our elements, rounding off to the nearest tenth. So copper is 63.5. Oxygen is 16, right? Grams per mole. So we divide grams by grams per mole. And that's going to give us our molar amounts, right? But one thing we want to make a note of, and write this starred bit down up top, right? Copy that down. Don't round any calculations until the end, right? So just take all the numbers off the calculator, unless they go really, really far. If the numbers go to the end of the calculator, then go like 4 or 5 decimal places, but don't round off yet. right? Don't round to 1 or 2 decimal places yet because it could screw up your final answer. So when I do 88.8 divided by 63.5 grams, I get 1.3984 moles, right? Because grams over grams cancels out. And then 11.2 divided by 16, I get 0.7, right? Now, step 3 is we want to simplify our mole ratio, all right? So this is our mole ratio right here, but it's not a very nice ratio, right? 1.3984 moles of copper. For every 1.3984 moles of copper, we have 0.7 moles of oxygen. So we want to try and get this to a nicer whole number ratio. So how do we do that? Well, we want to divide all of those molar amounts by the smallest value. In this case, it would be 0.7. So we divide them all by 0.7. Why do we do that? Because one of them is going to come out to be 1, right? So that's a nice number. And then we see what we get from the other one. So 1.3984 divided by 0.7, we get 1.996. It keeps going on. All right. So now is when we round. Now we round to the nearest whole number. Okay. So they're always going to be really close to a whole number, like this 1.996, or maybe it would be like 2.004, whatever. If they're not, then we got to do something else. All right. But in this case, 1.996 rounds off to 2, 1 rounds off to 1, and we're left with a 2-to-1 ratio. Okay. So now, if the decimal doesn't round off to a whole number, then it's probably going to be close to 0.5, right? If the decimal is close to 0.5, then round to 0.5. And I'll show you how to take care of that on the next practice problem. Okay. So if the decimal is close to 0.5, round to 0.5. Otherwise, it's going to be close to a whole number. If it's not, if you get like 1.27, then you screwed something up. Okay. I'm going to make these pretty simple where they're not going to go to any strange value. Okay. So what are we left with? A 2-to-1 ratio. So now we write our empirical formula. So there's 2 coppers for every 1 oxygen. So Cu2O. And that's our answer, right? That's it. So I'm going to give you the elements in the order that they're going to be in the formula. So you don't have to figure out who comes first or anything. You just got to write the element with its subscript. So 2 coppers and 1 oxygen. Cu2O. Done. All right. So let's look at another example here. Oh, wait. Well, let's go through our steps again, just to kind of sum this up and make sure we got this down. All right. So step 1, convert percents to grams. So I wrote a little 1 right over that. Step 2, we convert our grams to moles. All right. How do we do that? By dividing by our masses of our elements off the periodic table, right? Our molar masses, how much 1 mole weighs. We have that information on the periodic table. Okay. And then we're going to simplify our ratios by dividing by the smallest value. And then we can finally round, right? Now we round off our amounts to the nearest whole number, and that's going to be our ratio. So we can now write our empirical formula. So remember, don't round any of the calculations until the end, all right? Only round off at the end, and then go to your nearest whole number, okay? So let's look at one more. So if I have 43.7% phosphorus and 56.3% oxygen, what is the empirical formula? So I got to list my elements, P and O. Step 1 is convert those percents to grams. So I just take the percent and make it a G. So we got 43.7 grams phosphorus, 56.3 grams of oxygen. And then we're going to divide by our molar masses, which we have right on the periodic table. So phosphorus rounds off to 31.0, oxygen is 16. And we get 1.4097. And for oxygen, we get 3.51875. So if it goes past 4 or 5 decimal places, then you can cut it off, but otherwise, take the whole value. All right. Now, this is our ratio, but it's not simplified. So how do we simplify it? Divide them all by the smallest one, which is 1.4097. So we get P equal to 1 mole. And then for oxygen, we get 2.496 moles. What's that close to? half, 2.5, right? So now how do I get rid of the 0.5? So the way I like to think of it is think of it as like 2.5, all right? So if I want to get rid of that fraction, you just want to multiply the whole value by the denominator of that fraction. So I want to multiply by 2. So if I multiply everything by 2, so I want to keep the same ratio, so I have to multiply all of my values by 2. So 2 times 1 is 2, and then 2.5 times 2 is 5. So by multiplying by the denominator, that's going to get you to the simplest whole number ratio, right? Which is 2 to 5. So what's your formula? P2O5, right? Not too difficult. So now let's go to the worksheet on the following page. Let's turn to page 6. And you have this top part where you determine the empirical formulas. So let's just do the top part here. Question 1, numbers A through F. So just do A through F, and then we'll go over it. So pause the video, do A through F, unpause it, and we'll go over it, and then we'll try the bottom part out. All right, so let's go over these. So for P8S6, right, so now we're reducing these to the simplest whole number ratio. So 8 and 6 are both divisible by 2. So that reduces to P4S3, right? B is already in the simplest whole number ratio, so it stays the same. Next one, 6 and 14. Those are both also divisible by 2. So that reduces to C3H7. Next one is already simplified, CO2. Right? Next one, 686. Those are all divisible by 2 also. So we get 343. Okay. And then the last one, 18 and 36, are actually divisible by 18, and we get CH2, right? So 18 and 36 are both divisible by 18, so we get 1 to 2 ratio, right? So that's determining the empirical from the molecular. Pretty simple. Now for the bottom part, this is practicing what we were doing on the backside of the notes that we just took, all right? So I want you to skip number 2. So skip number 2, and then just go right to numbers 3 and 4. So give those a try. So pause the video again, give them a try, and then we'll unpause it and take a look at the answers. All right, so here are the answers to these problems. So number 3, so number 2, the answer is KCl, but we said skip that one. Number 3, the answer is Na2SO4. And then number 4, this is one where you had to double it, and you get Al2O3, okay? So in number 4, you ended up with 1 to 1.5 ratio. So then you had to double it to get rid of that 0.5, and that brought you to a 2 to 3 ratio. Okay, so now notice in number 3, it's Na2SO4. Now we can't reduce the 2 and the 4 because don't forget, there's a 1 here. So all of the subscripts have to be reducible, okay? So 2, 1, and 4 do not have a common denominator. So make sure all of the subscripts are reducible before you go ahead and attempt to reduce it, okay? So this one is just Na2SO4, all right? And that is that. If you can do all that, then you are in great shape. See you next lesson.